Hi there, and thank you for participating in this new CATIA Jewel Talk. Today, I'm very pleased to welcome Daniel Pyzak. Here he is. Hi, Daniel. Daniel
Hello.
co-leads, yes. Daniel co-leads a team of process experts in mechanical industry for CATIA at Dassault Systèmes. And Daniel is also a CATIA addict. So some of you may have already attended some of his numerous CATIA Jewel Talks or CATIA user talks. And for those who couldn't, you can still watch them on the CATIA user community. I'll show you at the end how to proceed, and in the meantime, you can already join the community with the link below, go.fredays.com/CATIA. And now for today, Daniel will talk on lightweighting, a crucial topic in a world where we are all striving for more sustainability. So Daniel, the stage is yours.
Thank you, Anne, for the introduction. Hello, everyone. I hope you're fine. At least on my side, I am fine. I'm always fine. That's my problem, by the way. So this is the 21st CATIA Jewel Talk. It's not the last one, don't worry. The idea is it's not something new. It's just something that we put on the market a couple of years ago, but it's not that well known. And I think it's good for you to get a refresh of what we can do in terms of lightweighting, but not only, you will see. And there are multiple capabilities. I am only 20 minutes to show you as a teaser what the solution can do for you. And let's start with this very simple example. It's a bracket. It can be a so-called fitting bracket. You have many of them in every product you can find in the industry. So it can be in an airplane, it can be in a car, in industrial machinery. And let's see how we can, with CATIA, reduce the weight, but also maximize the stiffness of this particular bracket. Okay, let's start. So this is maybe a CATIA V5 model. It can be also a step file or any other type of data. And we enter an app called CATIA Structural Generative Design. It's also, by the way, the name of the role containing this particular app. And let's start. So you will see that everything I'm doing is done inside the same application. Okay, I will never leave my application. Just to show you that it's really all-inclusive. Everything you need to lightweight a part is included in the same single application, Structural Generative Design. Let's start. So to start with, I will just deactivate some feature to give more space for CATIA to find the optimal lightweighting path. Okay, typically this is mainly the so-called design space, the allocated volume in space where I will design my part. A part is never alone; it's surrounded by multiple parts within an assembly, and this is a space where I can create my new design. So this is my design space, and I will enter this wizard. I will do a topology optimization, and I can select what type of target I'm looking for. Maybe I would like to maximize the lowest frequency for a given mass. Maybe I would like to minimize the mass, but of course, while respecting some constraints like maximum von Mises stress, for example. In this particular case, I will use the first one, which is maximize stiffness for a given mass. Okay, I have a wizard. You see on the right, I have a wizard, and I just have to follow step by step from the top to the bottom, all the steps to be able to perform my optimization. Okay, so first of all, I select the part, of course, and CATIA will analyze the part for me and find out that there are some area which are holes, drillings. Typically, this is mechanical interfaces with the surrounding parts, and he proposed to me to protect some area around the holes because I do not want those guys to be too thin. Okay, so let's select the values that he proposed to me, an offset of 3 millimeters. This is my geometry, my starting geometry. And then I will select, of course, a material. Let's go for a titanium material. We can use any type of material. And CATIA show you, okay, now this is my part, and I will define my boundary condition and my loads, okay? So for this particular example, my boundary condition will be a fastening condition, okay? So I will use a connection, and I have multiple choice, and I will select a virtual bolt. So the virtual bolt will generate a contact in terms of finite element analysis, and I define the axial stiffness and the shear stiffness, okay? And of course, the diameter of the nut and the bolt. CATIA is smart enough. He found out that there are some similar holes with the same diameter. He proposed to me to replicate the bolt definition. It's what I'm doing, no problem. Now I define also my loads. And for this case, I will select a remote force located at the center of gravity of those 4 holes and from a given magnitude and a given direction. You can have multiple load cases. For example, I will select another one with the same location, but a different direction and a different magnitude. And then you can combine the various load cases. The topology optimization that will be run by CATIA will be a compromise between all those load cases. You can have 100 load cases if you want, but it really will be the compromise, okay? So it's really averaging all the load cases. So this is my definition of my boundary condition and my loads. And I will add some constraints. I will show you later on what type of manufacturing constraints we can add. In this particular case, again, I will, to start with, no manufacturing constraints, just a shape constraints. I would like the shape to be symmetrical, even if the boundary condition and the load are not symmetrical, okay? I select my plane, here it is. This is my symmetry plane. And I will run my optimization. Before that, remember, the topology optimization is we are using Abacus as a finite element analysis solver. We are using our engine for topology optimization called Tosca. Both Tosca and Abacus are completely embedded in CATIA. This is a tool for mechanical designer, okay? So it is made simple. So there will be here just the finite element display, okay? You can play with some parameters to manage the size, the type of elements, but typically we take the value by default. Here in this case, I will select a target of reduce the mass by 85%. And then I can run my simulation. The simulation can be run on my desktop or laptop. We can use HPC server that we have that you might have in your company, but you can also use a cloud computing capability. Everything that I'm showing right now is running on premise with your own server or on the cloud. I'm here on the cloud. I can compute. And this is the topology optimization running inside CATIA. You see how the material is removed step by step. And the optimization is converging. And I will get a result. Cool. I maximize the stiffness. I reduce the mass up to 85%. And this is the result. And this is, in fact, still a finite element model. What you see in green is a boundary between what is considered empty or void and what is considered as plain element. Okay, you can play with this boundary. By default, it's 0.5, but you can play a little bit. You can make thinner or thicker branches. That's your decision. Usually, we do not touch that, but you can. Sometimes you can avoid orphan branches like that. And once you select, automatically, CATIA is computing a solid. This is a solid. He warped or created a subdivision surface on the so-called bionic shape, and he reincorporates all the mechanical features like the holes, the pockets, inside this subdivision automatically reconstructed surface. You see the quality of what has been done. It's quite nice. It's still, of course, a concept, but it's high quality. Sometimes you can, this is a solid, so you can mill it, you can do a drawing, you can step out, you can validate by simulation. It's, by the way, what we will do. I will just now, in one click, run a simulation to check that everything is fine. So now it's not just a simulation, static analysis. He kept all the definition of the setup, the boundary condition, the loads, he knows the material. You just have to remesh, of course, the part to do the validation. So everything is fine. You have nice tool inside the app to check the result. Here, the von Mises stresses. And once this is done, it was fast. I have time to, let's say, add now other constraints. So I will just create a new case, and I will add one constraint, a manufacturing control constraint, which is the part will be cast. So I will create a casting part, and I define in yellow here the direction of the pulling direction. Okay. I will rerun my computation, and automatically you get a new shape. You see, it's very, very, very different without manufacturing constraints, just with the cast constraints. Very, very different shape. Same steps. You can automatically create the solid out of it. You can validate by simulation that everything's fine. Now I will change and make another case, and I will just change the constraints, and then I will select milling constraints, 3-axis milling constraints. What you see in blue are just the 3 directions of your milling machine. And I run my optimization. And this is what I got. Okay, different shape again. And then, just to finish, to show you what we can do also cast, plastic injection, extrusion. And here in this case, I will just use additive manufacturing. So I will select the printing direction. So let's say I will print the part this way. The vertical of the screen is the printing direction. And I will enter the famous angle to avoid where we put support in the printing machine. So the famous angle is between 40-45 degrees, depending on the machine. Here I put 45 degrees. And the beauty of what CATIA will do is that it tries to create a shape which is self-supported. No need for support. At least it minimizes the area to be supported. And this is what we got. And in the tool, we have also a tool to check if you print it this way, this direction, where will be the supported area. So you see they are displayed in yellow. So very, very limited area, probably no need for support, only at the bottom of the part, obviously. Okay, that's it. You see the quality of what is done. You validate by simulation because it's almost a validation for free. It's very simple. And now you can compare. You select the various options you would like to compare. I will select 5 of them: the legacy part, the cast part, the milling part, the free of manufacturing constraints part. You can put priority of the various KPI. Maybe the weight is more important than the other. And CATIA will compute the best score and will tell you, Daniel, this is the best score. Of course, very important criteria is if you want to create only one part, additive manufacturing will be probably the best one. But if you want to create 1,000, you will probably use a milling one. So let's go, and we decide to go after the milled part. And let's convert now this geometry into, which is still a preliminary design, into a final parametric solid in CATIA. For that, we have a dedicated wizard. And you will see that for almost the first time in the life of CATIA, we introduce artificial intelligence, AI, in CATIA. So let's have a look. So this is the 3 directions of the milling machine. So for every single direction, we will compute a silhouette of the part along the direction. First of all, we have also computed the stock that we will use to mill the part. So first direction, first silhouette. This is a silhouette which is computed. So far, this silhouette is only set of polyline, okay? So now the user will have to, let's say, assimilate all those shapes to maybe a circle, maybe an oblong, maybe a polygon with fillet, maybe keep this as it is, a spline. And you will see that it's where we introduce AI in CATIA. So let's start. I select my outer contour, and you see I have multiple options: polygonal, primitive, line and arc, spline. So you can first do it manually if you want. I will define my spline. For the outer contour, I will define some primitive, like maybe a rounded polygon for this particular inner contour. And what has been introduced very, very recently is the fact that we train machine learning to find out for the user the best canonical profile circle, oblong, polygon with fillets, whatever, for you. So this is very, very new, and this is very, very efficient. So at the very end, you have a completely fully constrained sketch, and then we will just extrude the sketch along the milling direction, do exactly the same thing on other directions, and combine those three extrusions with a Boolean operation. So here you have AI inside CATIA to help you to quickly reconstruct detailed, solid parametric model from the result of a topology optimization that has been performed very simply, as you saw, inside CATIA. So finally, you have this solid model. You can then use the solid modeling capability to finally fully detail the model. You can validate the simulation, and that's it. Now, let's imagine, okay, typically when you are doing topology optimization, when you are reconstructing a model, human being add material. It's always not inside, but outside the shape that has been computed from the topology optimization machine. So the idea is now to reduce, to gain further weight by running a parametric optimization on the parametric model that CATIA helps you to design so quickly. So I will define the three parameters, L1, L2, L3, that will be used to be optimized. Okay. You see, this is this dimension here. This one. So this is the three parameters I will try to optimize to reduce as much as possible the weight. Okay. And now I will go to my an app. I changed app for now. I will go to an app called Parametric Design Study. I will define my design variables, the one I just showed you, L1, L2, L3. I will then, more important, define also the response variables. Maybe it will be the maximum stress, maybe it will be the maximum displacement, maybe minimize weight. Okay, so you define your response variable, the mass, and so on and so on. And then CATIA, and Simulia in this case, will run as many variants as you decide for the three variables. Okay, so for example, for one variable, you have a starting value, a finishing value, and a step in between. You see here, there are 27 different variants. If I select some parameters for my three variants, here we are. He computes all of them, and then for every single variant, he computes finite element analysis, here structural analysis, and he will tell you, Daniel, this is maybe the one we recommend you to use, but you can also manually select the one which are, let's say, the more interesting for you, and you will be able, like we were comparing the result of the optimization earlier, you can also compare all of them or some of them in a detailed way and select the one which makes sense for you. And once you have selected a solution, you feed the parameters of L1, L2, L3 that you selected to update your design. Okay, this is clear. Let's see now what we can do further. This is, let's say, topology optimization, but as you saw, it was a massive part, and we used tetrahedral element for the finite element analysis and the optimization. But we can do the same on a sheet metal, constant thickness. It can be sheet metal design part, designed with CATIA sheet metal design application. It can be a surface designed by generative shape design inside CATIA. So sometimes you call it surface topology. For me, it's still a topology optimization, but on a constant thickness model. Okay, let's do it on this small cube satellite structure. This is outer casing. So we started, in fact, with this geometry, and it's a sheet metal design part. You can see it because there is a dual view. You can unfold it at any time. You can now also, of course, we'll select the mid surface because we will optimize on the mid surface. It will be no longer a tetrahedral mesh, but a shell mesh. You define what you would like to optimize, maximize the stiffness, minimize the mass. You select the area you would like CATIA to remove material. As I did it before, you will have to define the boundary condition, the loads, Here we have also virtual bolts. It's a little bit more complex example. Axial stiffness, shear stiffness. What I'm doing right now on a sheet metal design part, parametric sheet metal design part, can be also done, as I stated earlier, on a surface model made with generative shape design, for example. Let's imagine you are working on a body-in-white underbody panel. Okay, this is my boundary condition and my loads. You run the optimization. The previous example, it took 20 minutes to compute on my laptop with 4 cores. Of course, if you want to use up to 144 cores on the cloud computing capability of Dassault system, you can also do that. This is the result. This is a displacement. And we run the optimization. Here, we just validated that our setup was okay. We define a manufacturing control if we want, but in this case, it will be sheet metal. So, and this is a result of the optimization. And it's a sheet metal part. So you can, if you want, unfold and get an unfold view. And so it's still, we kept the parametric sheet metal design feature. And this is your lightweight microsatellite casing that you can of course cut or stamp from a manufacturing point of view. What we can also do in CATIA is not only to lightweight, but to optimize the size, the shape of beads. Okay, let's take an example for this very simple part. So we have the part, this is a sheet metal part. We can unfold the view. We will define again the boundary condition and the loads. We define the target. Maybe I will speed up a little bit. This is the area where we would like to protect the material, so not add the beads inside the blue, dark blue contour. Here I'm just defining my mesh. Important, it's a shell mesh. You can see it. It's really a shell mesh. And you get the optimization. What we are doing here is we are optimizing the position of the beads, okay, to make the part more stiffer, okay. This is the area I found out. We extract the outer shape and we create a stamp feature in sheet metal design. And again, as it is a parametric sheet metal model, you get at the end a parametric sheet metal model. Okay, we saw topology optimization on a single part for a massive part, for a constant thickness part, but we can also do the same at the assembly level. Okay, so how does it look like? So if you have an assembly, you can do exactly the similar thing, but CATIA will run a topology optimization of thick or massive part or constant thickness part. Here we have a mix of both, okay, 2 solid part and 1 thin part. And as we did earlier, it will run the optimization for every single part that you decide to lightweight, of course, inside your assembly. Here I will just describe you what you are doing, but it's exactly the same thing. You select the part, you select the material, if it has not been predefined. You select the boundary condition and the loads for every single part that you would like to optimize. You select the manufacturing constraints or other constraints like maximum stress, maximum displacement, stuff like that. You define the boundary condition, the loads, and CATIA will run an optimization for all of them. And of course, depending on the manufacturing constraints that you select, it will create, for example, some parts for additive manufacturing, some parts for casting, some part for plastic injection molding. If you are doing plastic part or casting part, you are also able to for example, to drive the thickness. Most of the time, you try to get a constant thickness. You can also control the dimension of the ribs, the spacing between ribs. So it's really a tool to do any type of part, whatever the manufacturing process you selected to produce actually the part. Here we are. I will probably go a little bit faster. Here is the final result. And of course, you can validate now by a structural analysis your design and your optimization. 2 parts made in additive manufacturing and 1 made in a classical conventional stamping and cutting process. You might say, hey guys, it's nice, but sometimes it's not really lightweighting that I am interested by, but a different type of issue or different type of problem. So let's go inside this plane. And I have inside this plane a HVAC flow splitter. Okay, I would like to distribute air inside the cabin. This is a shape. And let's start first by by analyzing how the air is flowing inside this splitter. So you define the boundary condition. So here, in this case, at the inlet. So for example, a mass flow, how much of flow will be generated inside the inlet. We do the mass flow distribution, 50%, 50% for both outlets, and we will run. So now it's no longer a structural generative optimization that we are doing. We are doing a flow-driven generative optimization. Again, it's also all-inclusive. You are inside CATIA. We are running Tosca for the topology optimization, Abacus for the fluidic optimization. You see here what is the actual behavior of the fluid. A lot of turbulences. It's not very, very efficient from a pressure drop point of view. So from that, we create the design space. The design space in this particular case is really the design space we are starting from to optimize the vein, the inside, the interior of the duct or the splitter in this case. So we have the design space. We define the boundary condition and the loads. In this case, it will be again maybe a mass flow inlet and some pressure at the 2 outlets. So in this particular case, I'm no longer in the app called structural generative design, but flow-driven generative design. It's a different app. We have customers using both. You will see that at the very end of the presentation. And once you have defined the boundary condition and the load, you can select what you would like to optimize. So I would like to minimize the pressure drop. And this is the animation of how the material is removed. What CATIA is doing right now is eliminating the zone, the area of the shape, which are creating turbulences. Okay, so it removes those guys, and at the end, like we did for the structural generative design, we will automatically reconstruct a CAD model. So it's a solid that you can further detail and further refine with all the tools inside the app. So here in this case, we'll just perform again an assessment of the flow analysis to check if everything's fine. So we really reduce the pressure drop. We really optimize the shape of the vein of this HVAC splitter. You can see here the differences. And the beauty of that is that you can combine that. Let's take now to finish a small hydraulic manifold block. And we will first start by optimizing the vein of all the shape of all those channels inside the hydraulic block. You start with the design space, you define the boundary condition, maybe the velocity of the fluid at the inlet, maybe the pressure at the outlet. You create as many shapes as you have channels. And from that, you will try to optimize the weight of the casing of this hydraulic block. One of the constraints for the optimization of the weight will be, of course, the pressure of the fluid circulating inside the various pipes. So this will be one constraint. Then you have also the constraints maybe of how the block is fastened within its environment. You define the geometry. Again, it's the same steps as what I showed you earlier. You get the concept shape. In this particular case, we will select additive manufacturing to make this part because it's a prototype. So we have both a shape which is optimized from a CFD analysis, computational fluid dynamic, but also from a weight point of view. So this is quite important. You see that we can combine, we can do multi-domain generative design. And this is just the end of my presentation. I don't know if you have questions, but maybe I give back the mic to Anne. Anne?
Yes, thank you very much, Daniel, for this very interesting presentation. So let's see if we have questions, but I don't see any questions so far. So I have a question myself for you.
Go ahead, Anne.
Thanks. How would you describe the kind of people who might benefit from either structural generative design or flow-driven or function-driven generative design, please?
Okay, it's a very good question. The tool has been developed with customers of the industry, of course, but for mechanical designer. So we are really targeting mechanical designer. It is true that this mechanical designer, either he has enough skills from an FEA point of view. I'm not looking for super guru in stress analysis, but he needs some skills, some background on FEA. If he does not have this background, he can, let's say, make a team. He can team with a stress analyst, which will help him to define, for example, the simulation setup or the boundary condition, or to analyze the result. But it's really a tool for mechanical designer, and we have customer using, or the tool is used by customer by mechanical designer. Sometimes even I know one of them in France, it's an industrial designer. He's making very, very nice geometry, but his background is design, industrial design. And we have also some customer who gave this tool to a stress analyst. By the way, if you want to tweak a little bit more the finite element, make more complex element, or change some stuff, make advanced topology optimization, like for example, address non-linear case, you can do it, but not with the tool I showed you. There is another role, which is called structural generative engineer, and it's for stress analyst. It contains everything I showed you, plus some other stuff to do much more complex. But this is really a tool for mechanical designer. And more, especially in France, we have people at the university which are trained on both CAD and CAE. So this is a perfect profile for the user in front of this tool.
Good. Yes, thank you. So mechanical designers, it can help them to collaborate and quicker and more efficiently, but they can also do many efficient things on their own. Okay. Well, maybe we haven't answered all the questions that you may have. So you can still comment or ask these questions in the CATIA user community and get in touch with Daniel. So let me maybe quickly show you how. So first, sorry, I come back to this slide. You have to flash this QR code or enter this URL, go.3ds.com/CATIA, and it will require that you create a DS passport, but it's very quick. And then this link will lead you to the CATIA user community. So this is how it looks. You have articles there, media, many videos, demonstration, and so on. And in the wiki, this is what I wanted to show you. You can find the series of CATIA Jewel Talks here in this section, CATIA TV webinar and talks. And here, for example, I click on this episode, the one we are broadcasting now. And this is where you can write your questions for Daniel. So that's it for me. Thank you, Daniel, for this rich presentation. And thank you all for attending. then yes, don't hesitate to comment so that we can know what you expect on lightweighting from Dassault Systèmes in the future. And well,
and I
goodbye
think
for now.
you notice that we introduce AI in CATIA, so it's
Yeah.
it's very nice capability. We will not stop at that level. We continue to do that. And again, thanks for attending. And don't hesitate. It's free of charge. You don't need to attend to go to the CATIA user community. And we will do some other CATIA Jewel Talk in the future, different topics. Maybe you can also propose some topics in
Yes,
this
don't
CATIA
hesitate.
user community that you would like me or my team or my colleagues to address. It will be, of course, very important for us to follow your subject of interest. So thanks a lot. I hope you enjoy the talk. At least it was a pleasure for me to do the pitch. And have a great end of day, beginning of day, depending on what part of the geography you are. And have a great one. Bye bye.
Bye. Thank you.